سلام مهندس. جان
Hey, Justin.
Hey, can you hear me?
Yeah. How are you doing?
Fine, and you?
Good, good. Do you want to test your
Yeah,
presentation?
I just need to close some windows just to.
Sure. Is that okay if I record your presentation?
No problem.
Okay.
Okay. Okay, can you see my screen?
Yes.
Okay, and full screen?
It's a bit blurry.
Blurry? Okay, because
Yeah.
of
You optimize for the video?
Yeah.
Can you go ahead? Go to the next slide.
Is it fine?
Yeah, I think so.
Okay.
The texts are not perfect, but I think it's fine. Oh, it's better now. Okay.
Okay, no, I think it's, yeah, we need some time just to get the
Yeah,
right.
yeah.
Okay.
Okay.
And the sound is good?
Yeah, I think so. You were submitting to CVPR?
No, not me, not
Okay.
this year.
Okay.
Because I think, I mean, this year, I think CVPR is still remains virtual.
Yeah.
So it's a bit.
You don't like virtual conferences?
I mean, nobody's coming, so.
Okay.
Did you attend the IROS, for instance?
IROS this year, you mean? No, it was virtual, right?
Yeah.
Yeah. No, I don't attend conferences as well, I think. But next year, hopefully, some of them will be in person.
Yeah. So I didn't know at all ICRoM. So it's a national conference in Iran.
Yeah, it is international conference, but most papers are national, I would say.
Okay.
And yeah, because it's a bit tricky nowadays for Iranian students to go for the conferences.
Yeah.
The robotics, I don't know how it's called, Robotic Society of Iran decided to initiate their own conference.
Okay.
It's been now, I think, 7 years, and this year I've been asked to, to present a workshop, and I said, why not?
Oh, it's cool. I mean,
Yeah, I think it would be very nice because there are many robotics researchers there, and they are not aware of this very nice software like Pinocchio. So I think it's gonna be a very decent help for them.
Oh, cool. Okay, nice.
Yeah, but I also advertised internationally, so I think there are people from other places who would join.
Okay.
Mm-hmm.
Hello everyone. Hello.
Hi.
I am from India.
Okay, great.
So I can recognize some names, but not.
Yeah.
So just a reminder, how long is it, the presentation?
So the whole thing with the Q&A should be 45 minutes. So it depends on you how much you would like to devote to questions.
Okay.
So ideally, I don't know, 35 minutes to 40 would be nice.
Okay, yeah, there is some part that I can not present if needed
Mm-hmm.
for questions. And otherwise, I think if people want to ask questions, I can also answer on GitHub, for instance.
Okay, yeah. Okay, so let me just first say something about the workshop. Hello, everybody, and thanks a lot for joining to our workshop. So in this workshop, we would like to present some very nice open source software and hardware for robotics, especially for locomotion and manipulation. So there has been a bit of change in the schedule. So Farbod Farshidian is not able to present today. He's a bit sick. So I swapped my turn with Farbod. So what happens is that now we will have Justin and Andrea, and then we have 1 hour of break, and then we resume. So this is the updated schedule. Also, I will try to record the talks if the speakers consent, and we will try to upload it somewhere such that people can watch them offline. So to be on time, I think we can start now. I'll introduce first Justin. First, I would like to thank Justin for accepting to present in this workshop. Justin did his PhD in Geppetto Research Group last CNRS. He did research on biomechanics, state estimation, and control of humanoid robots. Then he did 1 year of postdoc in the same team, and afterwards he joined the Willow team in INRIA in Paris as a postdoctoral fellow. And then I think from 2019, if I'm not mistaken, he is a permanent researcher in INRIA team. So Justin has developed very nice software for robotics. One of them is Pinocchio. Pinocchio is great. I'm using it on a daily basis. And it's about rigid body kinematics and dynamics and its derivatives. So Justin, we are looking forward to your talk, and we are very excited about your presentation. Please.
Okay. So thank
you.
So
one other thing. So let me just start the recording if it's okay.
Okay, fine. Yeah, go ahead.
Just okay. Perfect. Go ahead, Justin.
Okay, so thank you very much, Majid and Farbod, for the kind invitation, and it's a pleasure to be able to present our work on for another continent and people maybe who cannot access to official, to the main conference streams. So today I will introduce you Pinocchio, and which is what we can call a universal framework for controlling simulation in robotics. I mean, in the sense that is providing the essential block to build controllers or simulators. So the work I started in this team, which is a Gepetto team. So in fact, so yes, the odyssey of all the softwares that we see mostly today are coming from this team. So in this team, you can recognize Jean-Paul Lemont, which was the creator of the Gepetto team, and other researchers that you might know, so like Nicolas Mansour, which was another permanent researcher in the team, and then there is Andrea here. So we will discuss about task-based linear dynamics and how to solve it in the next presentation. There is also Joseph Mirabel, which is also one of the most important developers of the team at some point, and he did a very large, great work on developing softwares. So there is Steve Tono, who will present today things related to motion planning and Lagrangian motion planning. Thomas here will be presenting something related to the solo robot and the open hardware robot. And there is also, for instance, here James Sorrell, which is also playing an important role on maintaining all the software that we will present today. And I'm just here. There is also Olivier Stas, which is now the leader of the team, and which also contributes a lot together with Florent Lamiro here on the left on developing all this software. So all the ODCs of Pinocchio and other software are starting from this point. And so now I will start the presentation about Pinocchio. So what is common to all these robots is that they are rigid body system, and we can efficiently compute their dynamics because we have a very well-based frameworks to do that, and we understand totally or completely the maths which are behind rigid body dynamic systems and the kinetic tree that are defining these robots. So if I have to start with something, it's related to the physical problem. So on the left, I have the picture of a polyarticulated system, and I can write the dynamics of this system following the Lagrangian formalism coming from Joseph Louis Lagrange. And so this is depicted by these equations. So we can read that as a mass times accelerations plus Coriolis and centrifugal effect plus gravity is equal to the motor torque or external torques applied on the system. So for instance, if I have this equation, so here I can move the segments, but just with this equation, if I follow these equations, the system will fall down. And in order to sustain the body in the air, what I need to do is to create contact interaction with the ground. And this is done through the notion of external forces, which involves the Jacobian of the contact points of the foot on the ground, for instance, here. So in the community, we have, the main important book for solving efficiently all these equations related to Lagrangian mechanics is related to the work of Roy Feresten, which was one of the pioneers in the domain, and which introduced a lot of efficiency in solving these equations. So we want to solve these equations, including the external forces, and for that we have the notion of forward dynamics, which is a simulation, in fact, which takes as input the current configuration of the system, current joint velocities, control input, and external contact forces. And as the output, what we have is a joint acceleration. And we have the reverse function, which we call inverse dynamics, which starts from current configuration and velocity, plus a given desired, for instance, a joint acceleration and external forces. And we want to compute the torques that we need to apply on the joints to solve these equations. So the important thing is that all these quantities here, the mass matrix and the Jacobians, have an internal sparsity, which is due to the kinetic tree, in fact. And the whole ambition of all this algorithm is really to exploit at best the sparsity which is involved and induced by all these quantities. So this is the purpose of the rigid body dynamics algorithm. And in Toulouse, what we have done is that we have developed Pinocchio. So Pinocchio is an open source and efficient framework which implements most of the common rigid body dynamics algorithm that we will see today, and which has been written in C++ and which is coming with Python bindings. So here, this is just the link for the GitHub access of the project. So from an historical perspective, so the project has been started here at last NRS, and now the development of the project is led by so INRIA, which is the French National Institute for Research in Computer Science and Mathematics. And so what we are doing now in Paris is that we have started to build a robotics team together with computer vision and machine learning in order to solve advanced robotics problem. So from a timeline, so the project has started in 2015, where we have been implementing most of the common algorithm coming from the book of Roy Firestone. And then we are starting in 2018 to deploy some contributions to have our personal contribution in the domain. So mainly the efficient analytical derivatives and also the notion of contact dynamics. And now what we are trying to work with is to build an efficient and principled differentiable simulator, and also going towards to real-to simulation learning. So we have a lot of users using Pinocchio, so both from academia or industry. So, so for instance, Max Planck, I didn't mention it, but we can put Max Planck on these pages, or the team of Ludovic Rigetti in NYU. But we have we have a lot of end users, so like Airbus, PAL Robotics. I think many of us know PAL Robotics, which is one of the most influential robot provider in the world. Wondercraft, which is a French company which is building, for instance, exoskeleton. We have Bosch, we have so INRIA, CEA, which is a French national agency for nuclear research. We have MIT, SoftBank Robotics, CNRS, and we have also new companies like Arrival or Covariant, which are also based on Pinocchio. So the question is that in the community, there is already a lot of framework which implements rigid body dynamics algorithm. And the question is Pinocchio just yet another rigid body dynamics library? The answer is yes, but not only. So in Pinocchio, we have a lot of features. So a lot of features that I won't all introduce, but I think it's important to have in mind. So we can support a number of joint primitives, so like revolute, prismatic, free fire, and so on. So we are able to handle the complex sparsity of the kinetic tree via the Firestone algorithm in majority. So in addition, we have developed our own advanced rigid body dynamics algorithm, meaning that we have supersede the algorithm by Roy Firestone by just improving also their efficiency. So we are able to deal with Lie group, which is a very important topic in robotics if you want to work on the right geometry and the right manifold. So Pinocchio is totally compliant with Lie group formulation, and which is a bit a unique framework in this domain. So we have also the notion of analytical derivatives for model predictive control mostly. We have also the notion of automatic differentiation, so meaning that if you want a derivative of something which is not where we don't have the analytical derivatives, we can still use automatic differentiation, and we have a lot of frameworks which are now plugged to Pinocchio. We are also compliant with the notion of source code generation, which means that we can generate codes for a specific system architecture, which is to lead to efficiency. So we have Python bindings for fast prototyping. We can do multi-thread computations. We also support collision detection, and for that we have a main contribution thanks to Joseph Mirabel on improving FCL library done by Dinesh Malhotra at the beginning. And also we have a lot of, we can support a lot of nomenclature to describe, to depict robotic system like URDF, SDF format, and so on. So how we write algorithm in Pinocchio, and we use a central paradigm, which is the strong splitting between model and data. So the model is a model of the robot, in fact, and with a lot of quantity which remain constant. And data are just a garbage storage of all intermediate quantities, which is required if to avoid online memory allocation, for instance. So in Pinocchio, we have this notion of algorithm, so like the forward or inverse dynamics, and all the algorithms are fully templatized by the notion of scalar, meaning that you can always download an algorithm to use your own scalar type, for instance, for automatic differentiation, or if you want to do infinite precision arithmetics. So the notion of model is constant quantity, and we have the notion of cache variables, and then the notion of arguments, which comes afterwards. So we have many advantages of using this paradigm of writing algorithm. So for instance, the compiler can guesses what is constant, what varies, and which makes efficient the notion of prediction and anticipation on the CPU, meaning that we can improve the performances. So in general, in Pinocchio, we don't have at all any online memory allocation, which makes the framework very efficient. And using all this paradigm makes the writing of algorithm very natural and very easy in some sense. So Pinocchio in action. So Pinocchio, the naming is coming in fact from the Geppetto team. So Geppetto is the father of Pinocchio, and so we took inspiration from this story to name our framework Pinocchio. So as I mentioned, in fact, Pinocchio supports the notion of a source code generation, so which allows us to compile on the fly using the just-in-time paradigm to get the best performances. And so I just want to illustrate with this slide the fact that, for instance, if you take the Atlas robot here, just evaluating the inverse dynamics take like 3.7 microseconds. So the timings now are you can divide them by 2. They are dated back from 4 years ago. I need to rerun the benchmark, but I didn't have time for that. But now you can divide everything by 2 in some sense because of many improvements in the library. But if you do inverse dynamics, the natural call to inverse dynamics, for instance, is 3.7 microseconds. But if you do also the code generation of this inverse dynamics code, you can go towards 1 microseconds. So it means that code generation is very helpful if you want to also improve your efficiency. And so we can do that for all the functions in Pinocchio, in fact. And for instance, for the KUKA arm here, we can see that going with code generation leads to very nice performances of 0.2 microseconds. And today it's 0.1 microseconds to evaluate the inverse dynamics, forward dynamics, or the mass matrix of the system. So, and I think this feature is very essential. And if you are willing to go towards making your robot on an industrial line, I mean, this feature can be very essential if you want to embed your code on a very cheap CPU or computational card. So today I wanted to take the opportunity also to present some recent work that we have done around Pinocchio, mostly on solving bilateral contact problem. And so the notion of bilateral contact problem is related to the fact of having either contact with the ground or having closed kinetic loops in the tree. So for that, what we need to understand is that how we compute the contact forces or the constraint forces which are related to either contact interaction or closed loop constraints. And for that, in the literature, we have very different approaches to model the action of the forces. We can use soft contact interactions for the spring damper model, which is very a naive way of writing things, which is used, for instance, in the Bragg simulator of Google. But this feature has been developed in the 80s, 70s. But now most of the people are mostly relying on rigid contact formulation or mixed contact formulation as the one developed in Mujoko. So today I will just present you how we solve the bilateral contact problem, but in fact all what I have presented will be are now extended in the notion of unilateral contact model. So to understand the way we solve bilateral contact problem, I just want to remind some principles that are coming from physics, and mostly what we call the least action principle, which has been formulated for the first time by Pierre-Louis Maupertus. And so the guy just mentioned that nature is thrifty in all its actions. And what it means is that we have some basic principle which tends to minimize some quantities when the physics is in physics. And what is very elegant with this statement, which just wording currently, is that it applies for many physical problems going from mechanics to relativity. And so, for instance, if I throw a ball in the air at 21 and it reached this position at time t2, and this is a motion of the throwing of a ball, as we can see in nature. But what we can imagine is that we have an imagine a motion where in fact we have a virtual path followed by the ball. So this motion is not feasible. But in fact, to understand correctly what it means by the least action principle, we need to introduce the notion of action. And the action is nothing more than the integral along the path of the kinetic minus the potential energy over time. So for this motion, we can compute a given action, S1. For this path, we can compute another action, S2. And what the nature will tell us about this motion is that S1 is lower than S2. So this means that, in general, this statement says that there is a stationary point for optimality when physics is occurring. And this is this principle that we will be using for solving bilateral contact problems. So for that, we have contact forces here, and we have here contact interaction between the bodies and the ground. And the least action principles translate in robotics or in rigid body dynamics as this problem, minimization problem, where we want to find Q double dots, so the joint acceleration, which will minimize this deviation of the current joint acceleration with respect to a reference acceleration, which corresponds to the free acceleration of the system. So the free acceleration corresponds to the acceleration of the body if there is no contact interaction. And this matrix is defined by the kinetic energy with the mass matrix used as a weighted matrices for this L2 norm. So, and in addition, what we need to handle also is this notion of contact constraint. So we want the contact to be equal to 0 at this level. I mean, we want to have the constraint to be equal to 0. The problem here in this statement, in this formulation, is that we have variables which depend on Q double dot and variables which depend on Q, and which is not an easy problem to solve. And to make this problem solvable, what we need to do is to do time derivation of the constraints, which is called in the control literature as index reduction. And so by doing twice this time derivation of the constraints, we get something which expresses the constraint as a quantity depending on Q double dot directly, and something which does depend on Q and Q dot, which is a constant with respect to the problem formulation. So this is how we make appears a single problem, which is called an equality constraint quadratic program, and we will see now how we can solve this problem. The first question in this problem statement is, where do the contact forces lie? And for that, to understand this concept of contact forces, we need to introduce what we call the Lagrangian of the problem, still done by the same mathematician. So the idea of the Lagrangian is that it's a mixture of a cost function, so the initial cost function here, plus lambda transpose. So lambda corresponds to the Lagrangian multiplier, and which corresponds also to the contact forces, in fact, transpose with the equality constraints. So by introducing this Lagrangian, we introduce also the notion of contact forces, which are the dual variable related to the constraint optimization problem that we have here. So now we will see how we can solve this problem. And so for that, we need to derive the so-called KT condition of the QP, of the equality constraint QP. And so if I derive the KT condition for this problem, I need to compute the gradient of the Lagrangian with respect to the primary variable Q double dot, which is giving me something like that. I can do the same thing with respect to the dual variable, which is just the constraints occurring. And I need to make this gradient vanishing and so equal to 0. So now I have this set of equations, and this set of equations define what we call the so-called KT dynamics, which is on the left-hand side, we have unknown variables Q double dot and lambda c that we aim to compute. And the right-hand side, we have constant variables which only depend on Q dot, and tau, the control input. So the question is there exists some solution for this problem? And the answer can be one single solution, a unique solution, a redundant solution, or no solution at all. So this depends, in fact, on the rank of the Jacobians. So if the rank of the Jacob is degenerated, not full rank, then we might have an infinite number of solutions. And if gamma c does not belong to the range space of GC, we might not have any solution at all. So now I will just introduce the way we solve the problem in general in robotics. So for that, we can analytically inverse the system to obtain the solution. So the first things to do is to just take the first equation and to express q double dot in terms of the free acceleration plus something which is related to the contact forces. So this is possible because the mass matrix of the system is always invertible because it's defined by a physical problem where we have positive masses on all the links of the robot. Then we can reintroduce this q double dot in the second equation to have an expression which only rely on lambda c. So on this left part of the equations, we have the notion of the Dualistic Matrices, which is also called in robotics the inverse operational space inertia matrix. So this is an important quantity in control, but this is also an important quantity in simulation, in forward dynamics. And on the other part of the equation, we have something which is independent from q double dot or from lambda c, which correspond to the free acceleration of the contact points. And then, if I inverse lambda c, I can get gamma c, sorry, so the Dualistic Matrices. I can get lambda c, and then from the lambda c, I can reinject that in the first equation to get q double dot and do the simulation of the system along the time. So the only strong hypothesis that I made here is that this Dualistic Matrices should be invertible, which is not always the case, depending on the rank of GC, as I mentioned earlier. So in order to avoid this kind of ill-posedness issue due to the lack of invertibility for this quantity, I will introduce the notion of proximal rigid contact problem, which is something that we have introduced this year at RSS, so the Robotic Science and System Conferences. So for that, I will first introduce the notion of proximal operators, which is something not very common in robotics because we are not mostly dealing a lot with this operator, but it's very common in machine learning, for instance. And the notion of proximal operators is just if we want to minimize, for instance, f respect to x and x belonging to a given set, the proximal operation is just a way to relax a bit the problem, saying that we want to have x not too far from an input entry y. And we have here alpha, which an archetypal parameter of the problem, which will be analyzed further in the discussions. And so the proximal operator is a way to smooth, in fact, our convex function f, and to make it strongly convex for the presence of this term. And in fact, if I need to solve the minimization of f along with respect to x, I need to iterate over this proximal operator as follows, with a given initial guess for x0. And in general, this leads to a cascade of simple problems to solve, which is good, in fact. But maybe we need a lot of iterations to converge towards the optimal solution of the initial problem. But we will see that for contact dynamics, this is not really the case, and just few iterations are needed to solve the problem. So how it applies for the case of contact dynamics is by smoothing what we call the dual of the problem by adding this term with a minus mu over 2. So mu now is, so I change the notation with, I use mu, but you just need to think about alpha. And I have added just a deviation terms, lambda c respect to lambda c references here with a minus. So this is an estimate of the contact forces. At the beginning, I can assume that the contact forces are equal to 0, and then I can, this is how I will initialize the problem. And so by adding this term, in fact, in the set of equations that we had before, instead of having a 0 here, which was making the problem not well posed, I'm adding this term, mu Tsad identity, which makes this KKT matrices here always invertible, and at the price of adding here on the right another terms. And so by iterating over this problem, by changing at each time the new estimate of the contact forces, I will converge towards the original problem. And this is a very good feature because we are recovering the solution of the problem that we aim to solve. So the problem in black here. So, and here on the right, I have a picture which shows the rate of convergences of the solving of this problem according to the optimality conditions of the problem and according to, depending on the value of mu. So the larger mu is the number of iterations will increase need for solving the problem. And with a small value of mu, like 10 minus 8, I just need like 2 or 3 iterations to converge towards the optimal solution. So it means that by just doing 3 times iterates of this algorithm, I convert to something which is very precise in terms of numerics. And I just need to do a single factorization of these matrices. And this is all. So is it okay at this time? So I'm not able to read the question if there is question during the proposition. So sorry.
I can ask the questions, but I think you can go ahead for now.
Okay.
You have only one question, so maybe it makes sense that you go ahead a bit more.
Okay, thank you for.
But can you be a bit louder, because some people are complaining that you're not loud enough or the sound is not clear enough.
It's not clear. So is it better?
For
now?
me, it's clear, but I don't know. Some people are complaining. Some there is not a consensus. Some people say it's not perfect. Some people say it's good. So I'm not sure if it's. For me, it's perfect.
So should I increase the sound?
Yeah,
or?
yeah. If you can do it, please do.
Okay. Okay. Is it better now?
I think so. For me, it's better also.
Okay. I hope there is no saturation. Okay. So sorry for that. So now, I mean, the way to solve the problem is remains the same. So the only thing that we change in the solving is the presence of these additional terms in the Delassue in the Delassue matrices, which now we can call that a damped Delassue matrix. And so the problem is always invertible, and we can convert towards the original solution. So this is the new way that we have introduced so this year to solve the problem. And now I will show you how we can, in addition, exploit the sparsity of the which is underlined by the problem in its own. And for that, I will take inspiration from the work of Roy Firestone. So Roy, among all the contributions that he has provided to the community, he introduces something related to the Cholesky decomposition of the mass matrix. So the mass matrix depicts a sparsity pattern which depends on the kinematic tree. And in fact, by introducing a UDUT, so upper triangular decomposition of the mass matrix, he shows that we can get something which a decomposition which keeps the sparsity pattern of the initial mass matrix. And so in the end, we can easily invert the mass matrix as the price of something which is O(n) square, n being the number of bodies of your system. And while if we were using something which is a dense Cholesky factorization, we will get something which is in n cubed. So here we have a very efficient way to compute the inverse of the mass matrix without directly computing it. And we can do the same. In fact, we can extend this work to work with the KKT matrix here on the left. Just for that, we need just to rearrange a bit the terms by working with the mass matrix on the the lower part of the matrices and putting the relaxation here, mu times identity, on the upper block part of the system. And so for that, we have introduced in the same work as at RSS this Cholesky factorization of the mass matrix, of the KKT matrix, which is an extension, in fact, of the work of Roy Firestone to account for the whole sparsity pattern of the KKT matrices. So the sparsity pattern is due to the mass matrix first, is also due to the Jacobian of the constraints here that we have, and which is also due to the fact that here we have something which is a mu time identity, which makes the sparsity diagonal. So in addition, what we have shown in this paper is that we can also, from the KKT, from the Cholesky decomposition of the KKT matrices, we can recover a lot of byproduct required for control. And mostly we have, as output, a direct way of computing the Cholesky factorization of the Delassue matrices, which was not possible before. And so this is a very new thing. And I do think that this feature can be essential if we want to efficiently solve inverse dynamics or forward dynamics problem. So as I mentioned, all these things have been introduced in this paper, which is now accepted and which has been presented this year. called plane-sparse resolution of constraint dynamic equations. So just we have several benchmarks in this paper, but I just want to illustrate a bit what we gain by using the proximal reformulation plus an efficient way of capturing the sparsity of the problem. Is that we have here in green, this was the original formulation of solving the problem, which was the state of the art at this time. So for instance, for the Talos robot, which is a robot with almost 40 degrees of freedom, so involving constraint with all the end effectors, so hands plus feet on the ground. And with the new formulation in orange, we have just divided at least by 2 or even by 3 the timings, so which is very good. And in addition, we have also proposed the code generation of this algorithm, and we can get we can save 10 microseconds for solving the problem. So we have something where we can handle very large, complex interaction, and we are able to solve that in the scale of 16 microseconds, which is, I think, very good, and which is a problem. So this is some results. So here we have the animal robot, which is with 4 contact points with dimension 3. We have the Talos robot with 4 contact interaction of dimension 6 with the hand and the feet on the ground. And here we have the Cassie robot, which has contact points interaction plus kinetic loops. And now we are able to handle in Pinocchio this notion of constraint system, which is, I think, an essential feature for advanced robotic system. So I will shortly introduce you this notion of analytical derivatives, which is one of the main features of Pinocchio and very essential, I think. So the notion of analytical derivatives is just when you do, for instance, for optimal control, like Carlos will present today. We need to compute, for instance, either the derivative of the inverse dynamics or the forward dynamics with respect to the entry quantities like q double dot, and lambda c. And these Jacobians are required if you want to solve numerical optimal control problems. So in the literature, there is different approaches to compute these things. For first, there is finite differences, which is very common, very simple to use, but which comes at some which are not efficient and which are also sensitive to numerical rounding. So if you want to be precise, you should avoid this kind of approaches. But I mean, at least you can work with black box system. You can also use arithmetic differentiation, and the simple idea is to use a chain rule formula in order to decompose the graph of computation and to compute the derivative of all the elements composing the graph of computations. So we have efficient framework, relatively efficient, which are very accurate, but in some contexts, it requires specific implementation. And in addition, they are not able, in fact, to exploit what we call the spatial algebra aspect of the algorithm. And so just to illustrate that, so what I call the spatial algebra aspect of the rigid body dynamic algorithm is, for instance, if you want to compute the time derivatives of the mass matrices, of the rotation, for instance. So rotation matrix is defined by 9 components. So we can imagine that if you do autodiff over this matrix, you will need to do the derivation over the 9 components of the matrix. While we know from our basic classes on mechanics and kinematics is that the time derivative of these quantities is just the rotation matrix, which is applied on the skew matrix related to the angular velocity. And what we have done in Pinocchio is that we have developed a not yet automatic, but almost automatic way of enrolling the equations and to compute the derivatives of, for instance, the RNA algorithms by deploying the arithmetics for deriving the derivative of these expressions in all its content. And in addition, we have introduced an efficient way to get algorithms which are with a low complexity of O, which is normally if you do that naively, you will get something in O n square. And in fact, in So 4 years ago, we have introduced something which is just the product of the number of bodies times the depth of the kinetic tree. So meaning we have something which is very low, and so this is what we have implemented 4 years ago. So just some benchmarks. So now they are very old, but you can divide all the timings by 2. Again, this is the same story. So for instance, if I take the biggest robot like Atlas, so evaluating the forward dynamics took at this time 9 microseconds. Today is 5 microseconds. We can compute the derivatives in 45 microseconds, and the timings for the finite differences were more than 400 microseconds. So it means that it's better to use analytical derivatives than to move forward with this thing. So for instance, this is an iteration of Carlos we will present I think today, and which is which is using analytical derivatives for the crocodile pipeline. So Carlos will introduce that today. But if you want to solve efficiently this problem and you want to compute you need to get access to these derivatives and to fast implementation, and this is what Pinocchio is providing, and which is mostly rooted on the performance aspect of crocodile. So another illustration of this work of using derivatives and Pinocchio. This is not another work that I've done with some colleagues here at ICRoM and also with Nicolas Mansart. So the idea is that we want to recover from a YouTube video, for instance, of a human demonstration. We want to reconstruct the 3D motion of the humans together with the object being manipulated. And for that, we have introduced a word pipeline to automatically extract these things. And we use physics as a prior to reconstruct the whole body motion. And so for that, we first extract from the video a 2D pose estimation of the skeleton of the person. We also learn how to retrieve contact status of many limbs of the system. And also we extract the motion of the object. And from that, we solve what we call an optimal estimation problem, where we try to minimize the reprojection error between the 3D and the 2D while reconstructing the contact forces interaction. So this is what we are doing, and we have an ongoing work which has been published this month on transferring that towards robot motion. So this is some results. So here we have, so I will stop. Sorry, I will just freeze the video. Oh, sorry. So here we have a man which is manipulating an object. We can extract from that the object placement plus the skeleton, and here we can extract from that many features like the whole body motion and the whole skeleton motion. And this is something very automatic. So we will release soon the code related to that, which is extensively based on Pinocchio. So before I was considering bilateral contact problems. We can also work towards the unilateral contact problem, which is a bit more complex in the sense that we have some principles that are occurring, like the maximum dissipation principle, complementarity conditions, like the between force and motion, and also we have friction cone that we need to be handled. This is a complex problem to solve. So I won't go into the details on how solving that, but we will soon release an efficient approach for solving this problem, and we will introduce that within Pinocchio. So the thing is that this problem is non-convex, so hard to solve, and the non-convexity is due to the complementarity conditions. Here we have the Coulomb friction constraint, and here we have the maximum dissipation principle. And so we have first work on providing the derivatives of this problem, which are well posed and also very robust in terms of numerics. And this is has been proposed in this work of differentiable simulation for physical system identification. And so the idea is that we have developed a simulation pipeline on top of which we can compute the gradients information based on the Steiger projection algorithm. And so for that, we have developed efficient way of computing the derivatives and stable way of computing derivatives. And we can recover, for instance, with this pipeline, some physical parameters like the mass or the friction between an object and the ground directly from images. So again, this is a work strongly based on Pinocchio. And now, just to finish a bit the presentation, I will introduce you the future of Pinocchio. So what we are working on now is to work on GPU and FPGA code source generation, which is very essential if you want to deploy efficient algorithm on embedded system. We are handling a constraint system, so as I mentioned, with closed loop. So we are building now an open source robotic simulator. So it's ongoing work, but we hope that this simulator can be very useful for model predictive control and also for the reinforcement learning community. This simulator will be 100% differentiable and with very efficient derivatives, very similar to what we have done in the past. So we are trying to extend also the support of biomechanical systems. We are also working on code generation of robot controllers. We are also very compliant on features on demand. If you need the features and you think that it can be used by many people, we are willing to implement that, and we have engineers for that. And we are also trying to extend the notion of collision detection in general. And so for that, we will have soon some contribution on that. We will be appearing. Yes, and so this is a picture of the two teams with which I'm working today. So there is a Willow team and the team of Francis Bach, which is mostly related to machine learning and optimization. So thank you very much.
Okay,
and,
great. I think now the timing is great. So there is one question that asks, I think, so does Pinocchio offer any features that allow inverse kinematics dynamics while respecting joint constraints? I think for that, the person who questions should follow Andrea's presentation in the next one to see how that works, right, Justin?
Yeah, you're totally right. So so for the interdynamics, this is the work of the presentation of Andrea, of course. And for inverse kinematics, I think we have already a lot of classes on this topic related to Pinocchio. It's very easy with Pinocchio to do to implement your own inverse kinematics with your own features, and it's just I think 1 hour of work if you want to do that properly. But Tsid is also able to handle second order inverse kinematics in his implementation. So I think Tsid will be the right answer indeed.
Okay, I also have a question, Justin. So with the new bilateral constraint that you have with the forces, I think this your Pinocchio can be used now very efficiently for parallel robots as well, right?
Yeah. This is totally right.
Because there are many people who are working on the parallel robotics, and now I think with this way, I think they can use Pinocchio very efficiently for this reason, right?
Yeah, exactly. So for us, the objective will be to have a single framework, so Pinocchio, which will be able to handle many robotic systems. So going from legged robotics towards parallel robots or just a simple robotic arm. But we want to have a common framework for that, and we need to have to derive a new framework for a given robotic system. Yeah. So you're totally right, and this is our objective.
There's a new question coming now. There are 3 questions actually. First one says that does Pinocchio framework explicitly supports the equality constraint within the QP structure, as for equations of motion, for example, or do you assign it within tasks with high gains?
So in Pinocchio, what we have is indeed an equality constraint QP solver, which is only related to constraints. So we have an efficient way. So what we are implementing now, it's a way to embed all the type of constraints that we can have in robotics in Pinocchio, meaning that you will be able to solve naturally constraint system in Pinocchio involving and exploiting the kinematic of the system, structure of the system. So yes, we have an API which is under development, but which will offer this feature.
Okay.
And so the second question, maybe I can.
The second question is that does it solve the QP in the strict hierarchy or weighted prioritize structure?
So currently, so we are only solving equality constraint QP equality constraint problem, and so meaning that there is only a soft cost term plus a single constraint layer, and so meaning that it's a single hierarchical problem and not, but without weighted. It's not weighted. Extending that towards hierarchy, a full hierarchy will be a good thing to do, I think, in future. But this
Okay.
is not worked. Yeah.
The third question is that on your slide 30, number 30, you had some numbers about timings. Does this, so can you clarify how these timings are computed? Does this include, for instance, self-collision avoidance, contact stability, I don't know, equations of motion, all these things, or it's only, I don't know, inverse dynamics, forward dynamics, the naive version?
It's only forward dynamics, meaning that we just account for the contact interaction, not for the self-collision avoidance. And for the self-collision avoidance, I think you need to look at the work of, the presentation of Carlos. We will present Crocodile, which is an efficient approach to solve optimal control problems involving contact interaction, involving self-collision avoidance and so on. Sorry.
Okay, we have more questions, but I'm sorry this is too late because we are out. We need to start the next presentation. So thanks a lot, Justin,
Thank you
for
very
this
much.
nice presentation. And yeah, I hope to see more of your work in the future.
Okay, thank you very much. And if you have any question on Pinocchio, I think the best way will be to open discussion in the GitHub pages of Pinocchio.
Okay, so I'll stop the recording. Hey, Andrea.
Hey, Majid. Hi, Justin.
Hi.
Okay, do you want to share your screen, Andrea?
Sure. Okay, so can you see my slides?
Yeah, but it's not in the presentation mode. Is this okay? Yeah, it's fine. Do you have videos or not?
Yeah, I have videos.
Do you want to play them to see if it's good? Quickly. Yeah.
Okay.
Yeah, perfect.
Okay.
Okay, one more question. Is it okay if I record your talk?
Sure.
Okay. Okay, then I'll start recording and then I would give an introduction and then you can go ahead. Is it fine?
Okay, go ahead.
Yeah. Okay, the next speaker is Andrea Del Peretta. Andrea is an assistant professor in the University of Toronto from 2019. Before that, he was in Max Planck Institute in Movement, Generation and Control Group as a research scientist. He did a postdoc for 4 years in Geppetto team at La CNRS with Nicolas Mansa. And before that, he did 3 years of PhD plus 1 year of postdoc at IIT Genova. So Andrea has done a lot of work on locomotion and a lot of very useful software for robotics like task space inverse dynamics. And we are looking forward to your talk. Andrea, please.
Thanks, Majid. Thanks for inviting me. So today I'm going to talk about task space inverse dynamics, which is a name that refers both to a mathematical framework that is used for doing robot control, and it's also the name of a C++ library that implements this framework. So I'm going to dedicate the first half of the talk to introducing the mathematical framework, so the theory, and then the second half of the talk will be dedicated instead to the implementation and the C++ library. So first of all, what is task space inverse dynamics, or TSID for short? Well, it's a popular control framework, especially used for legged robots and robot manipulators. It was a very active research area from about 2000 to 2015. Then after that, more or less everybody converged to a consensus, and so research on that subject kind of stopped, or at least slowed down. And you can think of this control framework as something that is similar to trajectory optimization, if you're familiar with that, but where the horizon over which you're optimizing is collapsed to 0. So it's trajectory optimization without a horizon. So it's instantaneous trajectory optimization. What are the applications for TSID? Well, TSID is quite flexible. It can be used for in different situations. Like for instance, if you have a reference state trajectory that you computed using indeed trajectory optimization, you want to track this trajectory on your system, you can use TSID for doing stabilization. Or maybe you don't have a trajectory for the complete state of your system, you just know the center of mass trajectory, for instance, and the fit trajectory that you maybe computed using a simplified model. Even in that case, you can use TSID for doing trajectory tracking. Or if you want to track a simple geometrical shape, like you want to follow a circular trajectory with the end effector of your robot manipulator, then again, you can use TSID. Or if you want to do balancing, TSID has been used quite a lot for doing balancing of legged robots. So I have a couple of videos to show you, just to give you an idea of what possible applications of TSID could be like. So here you can see on the left, TSID was used as a controller in simulation, and it was compared to an inverse kinematics position controller. And they also compared two different applications of TSID with position control and with torque control. And in this case, it was used on a humanoid for doing walking. On the right, instead, TSID was used together with a simplified model MPC for generating the trajectory of the complete robot. So for going from the simplified model, which only gave a reference for the center of mass, to the complete trajectory for all the joints of the system. And in this case, it was applied to a quadruped. So going back to the presentation, can you see my slides?
Yes.
Okay. So I will continue from my iPad so I can draw these beautiful red lines. So as I said, I will spend the first half of the presentation discussing the theory of TSID, and then the very last part is going to be about the implementation. So let's go a bit into the details of what TSID is about. In case you don't know anything about inverse dynamics, let's start from the dynamics of a robot manipulator. So mass matrix times joint accelerations plus nonlinear effects, which include gravity, Coriolis, centrifugal forces, typically also friction could be inside that, equal to the joint torques, which are generated by the motors. So the problem we want to face first is to find the joint torques so that the robot configuration, so the joint angles Q, follow a reference trajectory QR, which might be time varying. And what you assume is that we know the dynamics, so we know how to compute M and H, for instance, using Pinocchio, and we can measure the state of the system, so Q and V. So the solution to this problem is actually pretty simple, and it's given by the so-called inverse dynamics approach. So we set the joint torques tau equal to M times V dot desired plus H. So if we do so, since M is always invertible, it's very easy to see that if we plug that here and we simplify, what we get is that in the end, V dot is equal to V dot desired. So now we need to choose V dot desired, which is very simple because we have a linear dynamical system. And so we can simply set V dot desired equal to V dot reference plus a proportional derivative feedback term, which compensate for errors that we might have in the tracking of our reference trajectory. So we just need to choose then a proportional and a derivative positive definite gain matrices. And as long as these matrices are positive definite, we can be sure that the system is stable. So it's going to be attracted by this reference trajectory. So this is the resulting control law putting it all together, which is known in the literature as inverse dynamics control, but in robotics it's also called sometimes computed torque control. And this is a special instance of the so-called feedback linearization method from control theory, because we are linearizing the system, as I just showed you in the previous slide. So this is all very old style control approaches, because this comes from the 50s, I think. But what has regained attention in more recent years is that you can cast this control problem as an optimization problem. The optimization problem looks like this. We want to minimize these two variables with respect to these two variables, tau and v dot, which are the joint torques and accelerations. Trying to minimize this cost function here, where you minimize the difference between v dot and v dot desired, where v dot desired is computed as before, subject to the dynamics of the system as constraints. And it's quite easy to see that the solution to this minimization problem is exactly the same inverse dynamics control law that we just saw in the previous slide. So you simply compute the optimal torques as m times the desired accelerations plus h. Very simple and actually not very interesting, because why on earth would we need to solve this optimization problem if you already know that the solution is this one? Well, there is no reason to do so. But this is going to be our starting point in order to solve more complex problems that take into account more constraints of our system. And the good news is that this optimization problem is a quadratic program. It's a convex QP, which can be solved extremely fast at 1 kilohertz, for instance, with using off-the-shelf open source software. So it's something that you can actually do inside a very fast feedback control loop. So one of the things that we can do to make this problem more interesting is that, for instance, we can add torque limits. So we can explicitly model in our framework that the torques of our robots are bounded. So we cannot apply infinite torque. And then the controller is going to take that into account. Similarly, if you're using electric motors, for electric motors, the torque and the current are proportional to each other. And so we can very easily introduce also bounds on the motor current. With a tiny effort, we can also introduce bounds on the joint velocities. We just need to assume that the acceleration is going to remain constant during the time step, which is a very reasonable assumption because the time step is so small that typically accelerations are indeed constant. So if we do so, we can represent the next velocity at the next time step as the current velocity plus dt plus times the acceleration. And by doing so, we can introduce also joint velocity limits, which are also linear constraints. So the problem is always a quadratic program, even after we added all these constraints. We could also apply the same trick for introducing joint position limits, so expressing the joint position limits on the next joint positions, which are computed by simply integrating the desired accelerations. But this approach actually doesn't work very well because it typically results in very high accelerations, which might be incompatible with the torque and current limits. And so in the end, you can end up with a QP that is unfeasible. So in this case, if you want to do things properly, there are better approaches. For instance, you can take a look at this paper, which I wrote a few years ago, that explains how to do this in a more precise way that doesn't lead to infeasibility problems. But long story short, there are some simple approaches to introduce also joint position limits inside the TSID control problem. So we just went from the standard old school inverse dynamics control approach, where you don't have any inequality constraint, to this more advanced approach, where you solve a QP at each iteration of your control loop, and you can bound the torques, the current, the joint velocities, and the joint positions. So your control framework is immediately much more advanced. Let's take one step further, and let's assume that now we don't have a reference trajectory in joint space, but maybe we have a reference trajectory for the end effector of the robot, or for the center of mass of the robot, or maybe for the orientation of the camera of the robot. Actually, anything that is a function of the robot state could go in this list. So if you have a reference trajectory for one of these quantities, can we still use TSID? Yes, of course we can. And actually, the change that we need to apply to the formulation is very small. We are always solving a minimization problem, which is a QP, over the same optimization variables, which are the joint torques and the joint accelerations, subject to the same constraints, which are basically the dynamics of the system. The only thing that we need to change is the cost function. Before, the cost function here was something like norm of Q double dot, or actually U dot minus V dot desired square. And now instead we are doing X double dot minus X double dot desired, where we have expressed X double dot as an affine function of the joint accelerations, which is very simple to do, just computing the Jacobian of the quantities that we want to control. So this is going to be either the Jacobian of the end effector, or the Jacobian of the end of center of mass, or the Jacobian of the orientation of a frame. And all of these quantities can be computed, again, using the Pinocchio library that Justin just presented before me. So a very small change, and again, we maintain the structure of the problem, which is a QP. Can we do more? Sure, we can. So let's talk a bit about under-actuation. So far, we have dealt with the dynamics of a robot manipulator, which is a typically fully actuated system. So you have one motor for each joint. And the problem takes this form here, where now I wrote down the dynamics in matrix form, but it's just the same equation we saw in the previous slide. The problem is that many interesting robotic systems are not fully actuated, they are under-actuated. So the number of actuators is less than the number of degrees of freedom of the system. So that's the case for all mobile robots, basically. So legged robots, wheeled robots, flying robots, underwater robots, they're all under-actuated typically. So how can you extend TSID to handle under-actuation? Again, it's a very small change in the framework. So instead of having here the identity matrix, we introduce this selection matrix S, which, for instance, for a legged robot would look like this. You would have 6 columns of zeros here in the first 6 columns, and then you would have simply the identity matrix. So this matrix is basically selecting the degrees of freedom of the robot which are actuated. And just by doing this very small change in your mathematical formulation, now you can handle a system that is under-actuated. And this was not possible in the original inverse dynamics control law. Another feature that is very often useful and that Justin just actually discussed in great length is rigid contact constraints. So especially if you're working with a legged robot, so a biped or a quadruped robot, the robot is almost all the time in contact with the environment. And very often these contacts are modeled as rigid because that's very convenient in practice. So when you have a rigid contact, you basically are introducing a constraint because the robot can no longer move in the direction of the contact because otherwise it would penetrate the environment, which is not possible. So what you can do is that you can model that constraint using a mathematical equality, which is basically saying that the contact points do not move. Then to introduce this inside the TSID optimization problem, we need to take the derivatives of this constraint because Q is not part of the decision variables of our problem. So you differentiate the constraint twice and you express it at the level of acceleration. which is basically the same as saying that the contact point accelerations are null. After you've done that, you can introduce this equation here as an additional equality constraint in your problem. But you need to do something more. In this case, you need to also extend the number of decision variables of your problem to account for the contact forces, which are going to appear in the dynamics through the use of the Jacobian transpose, which multiplies the contact forces in the dynamics of a robot that is in contact with the ground or with any actually part of the environment. So in this case, the problem has changed a bit more, but again, it maintains the structure of a convex quadratic program. So it's still an optimization problem that can be solved extremely fast using the same kind of solvers that we were using before. So it's not a drastic change. So once again, the main benefit, at least as far as I'm concerned, of using optimization is that you can introduce inequality constraints. So if we want to maintain the problem a quadratic program, then we know that we can introduce any linear inequality constraint. So any inequality constraint that is a linear function of the joint torques, the contact forces, or the joint accelerations. So for instance, now that we have contact forces, we can introduce friction cone constraints by linearizing them, so approximating the quadratic friction cone with some pyramidal function, doing something like that. And you can make it as precise as you want by introducing more shapes, so more boundaries for the pyramidal approximation. You can also introduce collision avoidance constraints, which are a bit more complicated. And of course, you can always use the simple constraints, such as the torque bounds or the joint velocity bounds that we described before. Another very important aspect is that very often, if you're controlling a complex robot, typically the robot is going to be redundant with respect to the main task that you want it to perform. So for instance, if you are controlling a 7 degrees of freedom manipulator, and you want to control the placement of the end effector, which is 6 degrees of freedom as a task, you have 1 degree of freedom of redundancy because 7 minus 6 is 1. If you have an 80 degrees of freedom biped and you want to control the placement of the 2 feet, that's a 12 degrees of freedom task. So you're going to have 18 minus 12, so 6 degrees of freedom of redundancy. So clearly, you would like to exploit this redundancy in order to optimize the motion or maybe to achieve some secondary tasks that are not as important as the main one, but still you would like to achieve them at their best. So in this case, which is very common in practice, you want to express a cost function for each of the tasks that you want to achieve. So we're going to end up with a list of cost functions, let's say from 1 to n. Each cost function is going to be a convex quadratic function like this one. And a very simple strategy to account for all these tasks at the same time is to sum up the cost function altogether, but using different user-defined weights, WI. So each task is going to have a different weight, which is a positive scalar that the user must define. And clearly, the higher the weight is, the more important the task is. And so the higher the probability that the task is going to be achieved with a great accuracy. So typically, we're going to assign very high weight to the tasks that are very important and very low weight to the tasks that are instead secondary. So the pros of this approach is that the problem remains a computationally efficient QP. So you just solve a single convex QP as you did before. The problem is that if you have many such tasks to achieve, then tuning the weights might be a bit tricky, because if you have weights that are too large and small with respect to each other, this might lead to numerical issues. So your QP solver might have a hard time finding a solution, or it might even fail. That is why there is another approach, which is a hierarchical multi-objective optimization approach. In this approach, instead of assigning a weight to each task, you assign a priority. So you're saying that task 1 is more important than task 2, task 2 is going to be more important than task 3, and so on and so forth. So after you have defined this priority list, you can solve a sequence, also called cascade, of optimization problems from 1 to capital N, where in each problem you're minimizing just one task function subject to the usual dynamics constraints, but you're also adding an extra constraint that says that the cost function associated to the task with a higher priority must remain at the optimal value that was computed in the previous optimization problems. So in this case, you're going to end up solving not one optimization problem, but n optimization problems. So it's going to be more computationally expensive, but the advantage is that it's going to be easier for you to find priorities than to finding weights, because you need to basically assign only an integer value to each task instead of a scalar real value. So you have many more options, so many more probabilities of doing it wrongly. So that's it for the theory of TSID. I don't know if there are any questions so far. Maybe Majid can.
I don't see anything, so I think
okay.
we can go ahead for now.
Okay, thanks, Majid. So let's now talk about the implementation of this theoretical framework in an efficient C++ library. So TSID is an open source library implemented in C++ with Python bindings, and you can find it on GitHub at this address. TSID relies on a few very efficient C++ library for its computation. So we use Eigen for doing linear algebra computations. We use Pinocchio, which was just presented by Justin, for anything that is multi-body dynamics. And we use AQuadProg for solving convex quadratic problems. So pros and cons of TSID. Well, it has some missing features. So with respect to everything that I've just discussed on the theoretical side, some features are not implemented in TSID. Probably the main missing feature is that we don't have the hierarchical approach implemented. We only have the weighted approach for doing multitask optimization. We don't have bilateral contacts yet, and we don't have line contacts, and probably there are many other missing features that are not implemented yet. But then we have also a very long list of advantages of TSID. It's very efficient, so you can solve the TSID control problem in less than 0.6 millisecond for a humanoid. It has been tested on humanoids and quadrupeds. It's an open source software. The design is actually quite modular, so it's very easy to extend, and we do extend it upon demand. It comes with Python bindings, so it's very easy to use it just from Python. It's very easy to install because it comes with Debian packages, so you can install it just doing sudo apt install name of the library. It comes also with a lot of educational material because I use it quite a lot in my classes on robotics, and I've taught classes about TSID in winter schools and summer schools, so the material is available online. And also another advantage is that there are not many alternatives available. As far as I know, the only one that I know of is this ARCA framework, but it has different pros and cons with respect to TSID. So TSID also comes with a quite active community that is supporting it. I'm going to give you some numbers. So in the 4 years that has passed since it was created, we have had more than 400 commits, more than 50 issues closed, more than 60 pull requests, and 35 forks of the library. So just in the last 2 weeks, TSID has been cloned 18 times, and the page has been visited 47 times, which is more than I expected. We have also quite a long list of contributors. I'm probably the main developer, and Justin is the second on the list. And I should also mention Guillaume, which provides a lot of technical support, both for TSID and actually also for Pinocchio. And then we have also a list of more sparse contributors, which are just contributing from time to time for very specific features from very different universities and research centers. So let's go into the core of TSID, and let me describe how TSID has been designed. So the key concept inside TSID is the concept of task, which is something that you would like the robot to do for you. And a task can be a motion task if it is expressed as a function of the accelerations, a force task if it is expressed as a function of the contact forces, or an actuation task if you express it as a function of the joint torques of the robot. Another key concept of the library is the concept of rigid contact, which is quite similar to a task, but on top of that, it introduces reaction forces into the optimization problem that you want to solve. So it's different from a task, so we need to model it with a different objects. And then you can create all the tasks that you would like your robot to perform. You can create the rigid contact associated to the contact interaction between the robot and the environment in case your robot is in contact with the environment. And you can put them all together inside this other object here, which is called inverse dynamics formulation, which is basically just a collector of tasks and rigid contacts, and that contains all the code for translating task and rigid contacts into a hierarchical quadratic program. So why a hierarchical quadratic program? Well, as I said, at the moment, TSID doesn't implement the hierarchical approach, but the API has been designed to support hierarchies. So in the library, you will see that we always represent quadratic programs as if they were hierarchical, even if we don't support at the moment the solution of hierarchical QPs. Then once you have translated the problem into a HQP, you have a class which is a HQP solver that is just a solver for finding the solution. So just very briefly, a few of the methods of the inverse dynamics formulation class. You have a method for adding motion task, a method for adding force task, and another for adding actuation task. When you add a task to the problem, you can specify the weight and the priority. So the priority is an integer, and the weight is a double, so a floating point value. You have another method for adding rigid contacts. And then finally, you have a method for computing the problem data. So for translating the robotic control problem into an optimization QP problem. This is a list of some of the tasks that are implemented inside TSID. You have a task for controlling the joint posture, so the joint angles, a task for controlling the position and orientation of any frame of the robot. So for instance, the end effector frame, if you want to control position and orientation of the hand or the foot of the robot. You have a specific task for the center of mass of the robot, another for the angular momentum, and another for the center of pressure in case your robot is walking on a flat ground. Then you have bound tasks, which are translated into inequality constraints. You have a task for the joint bound, so this is used for representing joint position, velocity, and acceleration limits. Another one for the actuation bound, so again, joint torque limits. And then you have an inequality task for representing the capture point inequalities. This is very useful if you want to do balancing on a legged robot. Yet another very useful feature is the mask. So every time you create a task with TSID, you can specify a mask, like we did here for an ST3 task, which is basically selecting which directions of the task you actually want to be active and which one you want to be inactive. So in this case, we are selecting the first 3 directions as active and the last 3 as inactive. And the first 3 correspond to the translation, so the position, whereas the last 3 correspond to the orientation. So basically, we are using a ST3 task, which would by default control both position and orientation to control actually only position. We could have done also the other way around and controlled only the orientation and not the position, or we could have also controlled a subset of position and orientation. Any subset would have been fine. And mass can be applied either in the local frame or in the world frame. So typically the world frame is going to be more common. Regarding the contact models, at the moment, TSID supports 2 contact models. One, when you have a contact between surfaces, such as the one between the foot of a humanoid robot and the ground. This is called contact 6D because it constrains the motion of the foot in all 6 directions, so 3D position and orientation. Because once the foot is in contact, it cannot move nor rotate. Then instead we have the contact point model, which is used when you have a point-like contact. This is typically used for quadruped robots because the feet of these robots is very small, and so it allows them to still rotate after making contact. So in this case, the only quantity that is constrained is the foot position, but not its orientation. Every time you introduce a contact in the formulation, automatically TSID also introduces friction cone constraints to represent the boundaries that you have on your contact forces. The friction cones are of course linearized by using as many edges for the pyramid as you specify. Each contact also introduces automatically a force regularization task, which is very useful for regularizing the contact forces and making sure that the solution that you get to your problem is not jumping from one iteration to the next one, which might happen if you don't regularize contact forces. And can also be used to, for instance, introduce robustness into the problem by keeping the contact forces close to the center of the friction cone. So a few words on the QP solvers. So at the moment, you have several different solvers implemented inside the software. None of them supports a hierarchy, as I was saying before. So inside the HQP problems, basically, you can have only 2 hierarchy levels. One corresponds to the cost function, and the other one corresponds to the constraints. So all the solvers are based on A-quad-prog, which is a modified version of the solver U-quad-prog++ working with eigen. To improve efficiency, we actually optimize this solver, creating 2 new versions. One is called A-quad-prog real-time, which is the fastest, but it only works when the matrix sizes are known at compile time, which might not be always the case. If that's not the case, you can use the other version, which is called A-quad-prog fast, which allows for dynamic matrix sizes and performs only memory allocation when you're resizing the problem. Otherwise, there is no memory allocation going on at solution time. So these are a very old benchmark that I did when I was still working at LAS. So in 2017, I did this benchmark on the computer of the HRP2 robot, which is a very old computer. So this is a sort of worst case benchmark. You can see that on average, I was able to solve the TSID problem for a humanoid in less than 0.6 milliseconds, even with a very high number of active inequality constraints. So I expect that by now, if you do the same on a modern computer, you should be able to be below half a millisecond of resolution time. Okay, that concludes my presentation on the implementation of TSID. So to summarize, why should you be interested in using TSID? Well, TSID is a very common control framework for legged robots and robot manipulators, but not limited to these two kind of robots, actually. It comes with an open source C++ library, coming with also Python bindings, which are very practical for bootstrapping the learning of the library. It can be very easily installed using Debian packages, so you can just do sudo apt install to have it running on your system. There is an active community behind it that is supporting the library, and it is being designed in a very modular way, so it can be easily extended. So even if some features are not implemented, it's quite easy to add them. And there is also quite a lot of educational material online, such as slides, videos, and examples, or for instance, this presentation, which will be made available online, I guess, that you can use in order to learn how to use the software. So I would stop here, and I would be happy to take any questions if there are any.
Okay, thanks a lot, Andrea, for this beautiful presentation. I think it was very tutorial-like, and it would be very useful for people. So yeah, please send questions on the chat if you have any. So actually, one question came to my mind when I was listening to you, Andrea. Does TSID support the bilateral contact, for instance, a hand grabbing the environment?
No, that was one of the missing features that I was mentioning.
Mm-hmm.
It's really trivial to support the bilateral contacts.
Mm-hmm.
We should just remove the friction constraints, basically.
Mm-hmm. But there might be some bilateral contacts that have friction cone. For instance, a hand grabbing a pipe. Then you have one directional friction constraint. So I think it's not a very trivial problem. There can be, depending on the degrees of freedom of motion, you can have different types of bilateral contacts.
Yeah. You can imagine very complex contact geometries that result in weird friction constraints, as you just described. Those are not implemented in TSID, but as I said, the design of the library is quite modular, so it should be easily possible to add them. For instance, the contact point model was added years after I developed the first version of TSID by Julian, and he was able to add it without changing the API. So I hope that even these more weird models should be feasible.
Okay, great. So I think we are exactly on time, and so we can end this part here now. Thanks a lot again, Andrea.
Thanks to you.
So just one change in our, so I think we are done, Andrea. So if you wanna go, it's fine.
Okay.
We have things to do, but for the people who are here, we need to